In this section, we're going to look at harmonic motion of a pendulum. Harmonic motion of a pendulum. The force responsible for this motion is, of course, gravity. So let's have a pendulum over here. Let's say the length of the pendulum is L. And let's say the mass of the object is M. So of course we can go back and forth like this over here. Okay. Now suppose this inclination angle is theta. Now the force responsible for this displacement is gravity, but the direction of gravity is downward and its magnitude is mass times gravity. Okay. But you see the displacements along this circular trajectory. So the component of the weight that's responsible for the motion is the component that's tangent to the circular trajectory over here. All right, that's called Fs. The other component would be the component supported by the tension over here. Okay, so we have the following. Now this force over here is the same as this one. Now since these two lines are parallel, these two angles are equal, they are corresponding angles. Okay, so if you look at this triangle, it's a right angle triangle over here. We got a weight mg over here. So this side over here, which is this one over here, is mg sine theta. Okay, so the force responsible for this motion along the circular trajectory is mg sine theta. Okay, that is this component. This is the magnitude of the weight, and this is the component of the force in the direction of the circular trajectory. Now you see the direction of this force is clockwise, but the displacement is counterclockwise. It's this way. So they have opposite signs. So since the direction of the force is clockwise or to the left, we have to put a negative over here. All right. So as it stands, this is not harmonic because it doesn't show that the force is proportional to the displacement. For the motion to be harmonic, the force needs to be proportional to this arc length displacement over here, to this arc over here. Okay, so we're going to make approximation to see if the motion is harmonic for small angles. All right, so we're going to make approximation for sine theta. If theta is very small, we can make the following approximation. We can say the sine of theta is approximately equal to theta. It's easy to see this approximation. Let's look at the graph of theta and sine theta. Okay, the graph of sine looks something like this, and the graph of theta looks something like this. This is theta, this is sine theta. So you see, for small angles, they're very close to each other. Sine theta is approximately equal to theta for small angles. Okay, now with that approximation, we have this component of gravity along the trajectory is negative mg times theta. Now we want to replace this angular displacement in terms of linear displacement, which is s. This one over here is the linear displacement s. Now if you remember the definition of a radian in angle, a radian is defined in terms of a central angle. So it is arc length s divided by the radius, which is the length in this case. So theta equals the arc length s divided by the length. That's the definition of radian. So if this theta is in radians, we can say that this force over here equals negative mg and s over L. Okay, so s is now our displacement, so we can write as follows: Fs equals the negative of, let's put this expression in brackets, times s. Okay, now look, this expression over here is a constant because mass is a constant, gravitational acceleration is a constant, the length of the pendulum is a constant. So it follows that this force is proportional to the linear displacement s, okay? And also they're opposite in sign. Now remember, a motion is a harmonic motion if the force is proportional to the displacement and opposite in direction to the displacement. Therefore, it follows that the motion of a pendulum is approximately harmonic for small angles. So the conclusion is motion of a pendulum is approximately harmonic for very small angles, So the motion of a pendulum is not exactly harmonic, it's only approximately harmonic when the angle is very small. Okay, now let's look at the relationship. We've got negative mg over L times S. So it's our constant, and according to our general formula, we have negative k, well, times S in this case. All right, so it follows that the force constant for this motion is this expression over here. Okay, so by comparing these two, we can say that the force constant equals mg divided by L. Okay, and we've seen that the force constant can be expressed in terms of angular speed, and that's given by mass times angular speed squared. Okay, mass cancels out, so we get the square of the angular speed equals gravitational acceleration divided by the length, and that gives us angular speed equals the square root of gravitational acceleration divided by the length. Okay, so this relates to the oscillation properties of the pendulum with gravitational acceleration and the length. And since omega is 2 pi times frequency, it follows that frequency equals 1 over 2 pi square root of gravitational acceleration divided by the length. Okay, and the period is the inverse of the frequency, 1 over f, so it follows that the period is 2 pi the square root of length divided by gravitational acceleration. Okay, so these are the formulas that relate the oscillation properties of the pendulum with the length of the pendulum and gravitational acceleration. So remember, a pendulum is not exactly harmonic, it's only approximately harmonic when the angle is very, very small. Now let's look at an example. Let's say an object, let's say maybe a pendulum. It's a pendulum. A pendulum has a period of 1 second on Earth. So the question is, calculate its period on the moon, where the gravitational acceleration is 1/6 of that on Earth. Okay, so I'm going to use subscript E for Earth and subscript M for moon. Okay, so in this problem we see that the period on Earth is 1 second, and we're being told that the ratio between the gravitational acceleration on the moon to the gravitational acceleration on Earth is 1/6. So if you divide the period on the moon by the period on Earth, we should get 1. No, talking about gravitational acceleration. So if you take the ratio between the gravitational acceleration on the moon and gravitational acceleration on Earth, according to the information given, that's 1/6. Okay, now let's write expressions for the periods. The period on the moon is 2 pi square root of the length divided by the gravitational acceleration on the moon. The period on Earth is 2 pi square root of L over gravitational acceleration on Earth. Okay, now let's take the ratio. The period on the moon divided the period on Earth equals 2 pi square root L over G on the moon divided by 2 pi square root L over G on Earth. Okay, and that equals 2. You see 2 pi cancels 2 pi, L cancels with L. That gives us the gravitational acceleration on Earth divided by the gravitational acceleration on the moon, of course, square root. Okay, so that tells us the period on the moon equals the square root of, remember this ratio over here, moon divided by Earth is 1/6, and of course Earth divided by the moon would be 6. Okay, this ratio is 6 times the period of the pendulum on Earth. But we're told the period of the pendulum on Earth is 1 second, so it follows that the period on the moon would be square root of 6 times 1 second, which is square root of 6 seconds.